Hi everyone, this is John Paul Raj and I'm here to solve one more paper today. This is another live stream, my second live stream, and today what we're going to do is I'm going to solve this the second part of the paper 6. Last week we solved the investigation part. This week I'm going to solve the modeling part. I don't even know whether anyone is watching, but whether not anyone is there, I'm here to solve the paper. I just love modeling papers. Okay, the modeling, the idea is to come up with an equation, but I think when I scan through this paper, there's not much of us coming up with an equation from the data that's given, but it's a very interesting question that they've framed for the June 2021 paper. This is modeling the part 2, okay, and I've explained how the paper is set up in the earlier stream where we did investigation. This is modeling. So let's just take a look at the question, okay. High river flow, that's what it's called. This particular modeling exercise is called high river flow. It says this task looks at estimating the probability of high river flows. Planners need to estimate the probability of extreme events such as high river flow. To do this, they use the return period R years. So the return period is in capital R. This is an estimate of the number of years before they expect another high river flow. Basically what happens is that if there's a high tide or a high river flow, the way to estimate when the next one is going to be. So obviously they are accumulating data, and that capital R is the return period, which probably suggests or gives an estimate of when will be the next time they're going to expect something similar. All right, a model for capital R is equal to n plus 1 over h, where n is the number of years where there are river flow results. So basically the number of years where they've got all the data, okay, that's n. H is the number of times that high river flow occurs during those n years. So how many times that crosses a certain level, that is called the high river flow, okay. I'm glad that Jalaj is here. Jalaj, thank you that you're here. But yeah, I thought there is no one here, but anyway, I'm just going to do it because, you know, I love to solve mathematical problems, and especially like these mathematical modeling, okay. So even if you're bored, just pull out a paper and just try doing it, okay. It's always great to see how accurate your equations are to come up with your equations, okay. But let's get back to this question. Let's look at that R again. This equation, or this R, is n plus 1 over h, and n is the number of years that we have all the data, total number of values we have on the data that these river flows have been measured and tabulated. And h is the number of times in that table, how many times we have this high river flow. The probability, now this is what we are trying to study, right? It says this task looks at estimating the probability. Yeah, that's what we're looking for. The probability of the high river flow occurring in any year is 1 over r, okay. So that r gives us the model for the return period, as I say, when will be the next high river flow, and the probability of a high river flow occurring in any year is 1 over r, okay. So this is an example that they've given, and then I think the questions will follow. The question says the example says on three occasions during a period of 65 years, and that's your n, all right. So n is going to be 65, and that h is that 3, okay. According to that formula they've given, right, n is the number of years that the results have been tabulated, and 3 occasions there was a high river flow that is greater than 4,000 cubic meters per second, so meter cube per second. So the return period, that capital R, return period for a water flow greater than 4,000 meter cube per second. Now this is something that is, you know, for a particular river, for any particular river, that's going to be different, okay. For this particular river that they're talking about, that's the mark, okay, beyond which it's considered as high. 4,000 meter cube per second, using that formula, capital R is 65 plus 1, as we said, it's n plus 1 over that h. So 66 over 3, that's 22 years. So apparently R, that return period, is 22 years. So the next time that they're going to have a return period, the next time they're going to have a high river flow is going to be 22 years, which means that the probability, as they said, the probability of a river flow greater than 4,000 meter cube per second any given year is 1 over 22. Okay, now what they've written here is also very interesting. They said that this is not very likely in a year, all right, but very likely in the lifetime of a bridge. Most bridges are constructed to last for 100 years, okay, and that's great, 100 or more years, right? So very unlikely to happen a year when you say 1 over 22, that number, but for the lifespan of a bridge, that might be interesting number, okay? So let's look at the question, okay? This says 6 because it's a continuation from the investigation part, from the first part of the same paper. We are just looking at the modeling part today. These are the maximum flows in meter cube per second each year for a small river, okay? So this is the data given, and let's first find out how many data points we have. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've got what, 24 such data points. Let me count it again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, we've got 24 such items. So we've got n is equal to 24. And then it says calculate the return period R for a flow greater than 100. Like I said earlier, for each river, that number might be different. The example that they gave, it was like 4,000 meter cube per second. And this is a small river. So 100 meter cube per second, that would be a high river flow for this particular river. So when we look at how many times has it crossed 100 in this data set, we've got, okay, that's 119 going across, there's none, this is 1, and this is 1. So 3 times, that's going to be H. That's going to be H. So 3 times, okay? So the return period, according to the formula they're given, capital R is 60, n plus 1 over that H. So capital R is going to be 24 plus 1 over the 3. That's a 25 over 3. It's okay even if it's not perfectly divisible. This is going to be 8 and 1/3. You can leave it like that. Okay. That's like after 8 years, you can expect a second or another high river flow for this particular small river. Use your answer to part A to find the probability. Okay, the probability, as we saw here in the earlier case, in the example, it's just 1 over R. So the probability is just going to be the reciprocal of this. The probability is just going to be 3 over 25. All right. Okay, moving on. Number 7. The probability of an event occurring in 1 year is P. The probability of an event occurring in 1 year is P. Write an expression in terms of P for the probability of the event not occurring. That's like the complement. Okay, so not occurring is just 1 minus P. All right, this may not be directly related, but because the question is about probability, so there it go. Okay, find the expression in terms of P for the probability of the event not occurring for 10 consecutive years. Interesting. 10 consecutive years. Here we have to recall the idea of independent events, because although this is not about probability, this is about the river and the high river flow, as I said, but because it's about the probability of an occurrence, something like that, I think this is just a refresher. This particular part of the question is just a refresher on the idea of independent events, because each year is independent. So because they're asking the expression in terms of P for the probability of that event not occurring, we already said that not occurring is 1 minus P. So not occurring for 10 consecutive years will be just 1 minus P to the power of 10. It's basically 1 minus P times 1 minus P times 1 minus P, 10 times like that. So it's 1 minus P to the power of 10. Explain why the probability of the event occurring at least once in 10 consecutive years is that expression 1 minus. Okay. Now, whenever you see something like at least once, they're saying, all right, at least once is like the complement of not occurring, right? So we already said in part 2 that not occurring is 1 minus P to the power of 10. So when you say at least once, that's like saying the complement of not occurring at all, right? Not occurring at all for the 10 years. So we'd say that is because they are complementary events. That's a good reason, okay? And I don't know why I wrote in red, but I've written it, so be it, okay? Because they are complementary events, from part A, you can say using result from actually part 2, okay? So 7A2, you can make a reference to that. 7A2, probability of the event occurring at least once in 10 years. 10 consecutive years actually is 1 minus that expression that they've given 1 minus. Okay, so I hope that is clear that this is just the complement of that result that we wrote in part 2. All right. Okay, any comments, any questions here? Nobody. All right, cool. B, all right, B says a model for the probability Y. Okay, so on the y-axis it is the probability. This is the probability you're looking at. Okay, a model for the probability Y of a flow greater than 130. Now obviously this is some other river we're looking at. Okay, a model for the probability Y of a flow greater than 130 meter cube per second occurring in a river in question 6 in the river. Okay, it's the same river we are talking about. It's the same river. Sorry about that. Okay, so 160 is not mentioned, but they've just that was just for 100, but they've made another probability, another equation. Here we go. That is the probability for the same river. Okay, it's the same river. 130 is the mark we're looking at. So anything greater than 130 meter cube per second occurring in that same river, at least once in the x years. So x-axis is the years, and the probability is along the y-axis is given by that model, by that equation. Y is equal to 1 minus 0.04 to the power of x. Sketch the graph of y is equal to 1 minus 0.04 to the power of x between 0 and 25. Now we have to use a calculator for this. Okay, I'm going to switch to the calculator here. Let me just switch to the calculator. There you go. Can you see the calculator? Cool. And you can just copy it down, all right, just as you see it on your calculator. So I'm just going to insert a graph page. Control doc will insert a graph page, and we'll enter the equation just as it's given. It says 1 minus. Okay, so I'm just going to enter it as it is. All right. Okay, it is 1 minus, and then bracket 1 minus 0.04. 0.04. Did I enter that correctly? 0.04 to the power of x. So there we go, to the power of x. Do I have it right? 1 minus. Yeah, I got that right. So the function has been entered correctly, but we need to make sure that the window settings are right. Okay. Now obviously that's why we can't see the function correctly here. So what have they given? They've given from 0 to 25. So let's just change that. Now as a habit, what I do is that I try and keep a little bit on the left hand side. Okay, so if you go on Windows settings, menu, Windows zoom, and Windows settings, what I do is x min, according to the graph which they've given us, is it's 0 to 25, right? But just for my reference, of course, when you draw the graph, you draw from 0 to 25, okay, as given in the question. But just for my own reference, what I do, it helps me. Okay, so these are just some tips, because I'd like to know what's happening, slightly before or after. So I just keep a unit before 0. So I'll start the x min from -1. So -1. And the x max, they said, is 25. So same way, I'll keep 1 unit more, okay, just for my own reference. The scale, I'll just change it to 1. The y min, in the same case, they said from 0, but they've not given us an upper limit. And sometimes this is the trick, okay. Let me just show that again. They've not given, can you see this on the question paper? They've not given. In some papers, I think this is what solves the mystery. Okay, so they have given us the maximum value for x here, but not given the maximum value for y. And that is, for students to figure out, play around with it and figure out when would you see a nice looking graph. Okay, and since we are talking about probability, can you guess what it should be? We're talking about probability, why this, it says y is the probability, right? So that should be a little hint. Okay, so if you're not able to see a nice clean graph, you know what's being represented on the y-axis, accordingly make that adjustment here. So I would say my y min, I'm going to keep it to -1 as before, as the x-axis, that is. And on the y-axis of the y-max, I'll keep it to 1. All right, I already told you why, as a clue, that is. And there we go. I make the change, and there I see the graph, nice and clear. All right, so all that we need to do is just copy it down as it is. I'm just going to take a screenshot, okay, of this graph. Capture page, and yeah, it's going to save that page for me and save. Okay, so we'll come back to this screen of ours, and let's see whether we can put it in here. Give me a sec. Where is this question? Okay, insert picture. Yeah, I'm solving it on OneNote, right? So one sec. This is the graph, I believe. If I insert it here in real time, does it show here? There you go. Can you see? I did it on my laptop, and actually it's showing on OneNote here. And let me just see whether I need to resize this here. Okay. Right, so that's the graph. Okay, basically you'll have to copy it down at the time of the exam. You got to copy it down, okay, as it is. And like I said before, although I made the measurements from -1 on the x-axis and on the y-axis, you need to copy it down exactly for what is given. Okay, don't do anything extra. All right, so then only, and then you'll get those 3 points that is allotted for that question. So that's the graph. Okay, this was only to sketch the graph. Okay, then it says, part 2 of the question says, let me go back to the graph here, the calculator. It says, find the number of years that pass before the probability of a flow greater than 130. This is the model for 130, right? 130 meter cube per second. Find the number of years before the probability of a flow greater than 130 meter cube per second first becomes greater than 50%. So you're looking at, when will it become greater than 50%? Okay, greater than 50%. Now there are different ways to do this. Okay, one is you can just draw y is equal to 0.5. Okay, so if I just go back to my calculator, and if I just hit tab and I just say 0.5, 50%, right? And there you go. I can find the point of intersection. The x value is the years, right? So this is one way to do it, that you can just draw 0.5 and then find the point of intersection. Basically you can go here. You can even do the analyze graph. I like the geometry one, all right? So if you have more than one point of intersection, it just helps with this geometry option. So once we've done that, you can see clearly that the point of intersection is 17 and 0.5. Okay, so that is 17 is the number of years, right? So basically it's like, it'll take 17 years, and only after 17 years will it be greater than 50%, becomes greater than the calculator. You could have done it another way also. There are different ways, of course. That's the beauty of solving these kind of modeling questions. On the calculator page, if I go here, I could still use nsolve. I can just go here, menu, algebra, and I'll pull out nsolve. And because it's already been defined there, okay, the graph was defined here as f1 of x, right? f1 of x. So I can just say nsolve, and I'll say f1 of x here. Okay, so f1 of x, and that must be equal to 0.5. Okay, comma x. That's the syntax for the TI Nspire. I just say control enter to give me in decimals. What do we get? I get 16.98. Okay, so the accuracy here is different because what is it set to? It's set to fixed 2. All right, I don't know. Can you see this? Yeah, you can see it's set to fixed 2. So if you make it 3SF, if you make it float 3, and the calculation mode also, if I keep it to exact, never mind, I can keep it to approximate. And now if I do that calculation again, what do I get? There you go, right? So there are two ways to do that. You can either use a calculator, or you can use the point of intersection method. Either way, you should come back to your notes and say, well, the number of years that it's going to take is 17. Okay. Working. How do you show the working? Well, on that graph that you've drawn, okay, I'm coming back here, you need to indicate where is 0.5. Okay, so if that's 1, obviously 0.5 is here. So you need to draw a horizontal line and show that the point of intersection, wherever it intersects, to make sure that that is 17, indicated that way. All right, so that counts as working. So every sketch that you see, everything that you see on the graph, make sure that it's almost like taking a screenshot. But obviously at the time of the exam, you can't do the screenshot. Okay, you draw and make sure that you've indicated. That will be the working, because there's 2 points for that. Okay, part 8, question number 8. All right, it says the table shows the probabilities of various river flows in a year at Waverly on the Missouri River in the US. Okay, flow in thousands of meter cube per second. So these are the different flows. Capital F is what denotes the flows. That's 2, 4, 6, 8, so on and so forth up to 22. And this is the probability. Okay, the table shows the probabilities. Okay, what is the probability of 2 meter cube per second? That's the probability. What is the probability for this flow? That's 0.85. Okay, that's how the table has to be read. Probability is denoted by small p. Okay, in this table. So you got 2 columns, capital F and P. Okay. All right. Do we have anyone saying anything at all? Let me just see. I just wanted to pause and see whether this. Cool. All right. A possible model for this data, or this table, a possible model for the above data is, now they've given something here, 1 p is equal to 1 minus k times f, where k is a constant. All right. Use figures from the table to decide whether or not this is a reasonable model. Okay, so they've given a model, p is equal to 1 minus kf, and f is the flow. F is the flow, and p is the probability. The reason I'm talking about that is because the earlier case that we saw, this one here, x was the years, right? X was the years, and p was the probability. All right. So keep in mind what we are looking at here. The data, p is the probability, and f is the flow in thousands. Okay, it's not the years this time. All right. So the model obviously is different. So it's p equals 1 minus kf. K is a constant. Use the figures in the table. So that means use the data in the table given to decide whether or not this model is a reasonable model. All right, let's check. Okay, so when P is 0.99, I'm going to do the calculations here, right? So when P is 0.99, what do we have? We got capital F as 2, right? Capital F is 2. Can you see this? Yeah. So let's just check whether it works, all right? And maybe find out what the value of K is. So with these values, we need to get, that's model is 0.99, should be equal to 1 minus K times the capital F, which is 2. That is 2K would be equal to 1 minus 0.99, okay? And then we can solve for K. Because we have access to the calculator, let's just do that, all right? So we go back to the calculator page, just enter it as it is, okay? Also, I think a way for me to show, the shortcut. So I know 1 minus 0.99 and the whole thing divided by 2 to get the value of K as I think my calculator is set to, it was set to approximate only, I think. So 0.005 should be the value of K for these values, that is 0.00005, okay? That's the value of K. Let me just show to you, okay? For P is equal to 0.9 and the first set, okay? Let's try for the next set. So we can write down when P is 0.85, the same thing I'm going to write down, okay? When P is equal to 0.85, the value of capital F is 4. F is equal to 4. So when you put it into that model, we'll get 0.85. Okay, same way we're doing 0.85 should be equal to 1 minus K times 4. Is that right? So that you should get 4K is equal to 1 minus 0.85. That should be 0.15. But let's do it in the calculator again. All right, so this is 1 minus 0.85 divided by 4. Again, let's switch back to the calculator. And the reason I'm doing is that, so that you can even see some of the shortcuts, how to use the GDC. So once you have the entry, you can just use the top arrow key, bring back that expression, and you can just make the changes there, okay? You can edit that. So it's 0.85, all right? And here we need 4. And when I hit enter, 0.038, and clearly you can see that the value of K is not the same, right? Value of K is not the same. So I can write in the value of K for these values as, what was that? 0.038. And why did it say the value of K is, why did I stress on that? Because it says K is a constant, right? Look at that. It says where K is a constant. So no matter what the data values are, if K is a constant, okay, then this should be true. This model, this equation should be true for all values, all right? So capital F and P, no matter which, we just tested with two values and it's not the same. So using the figures, as I said, we checked that the value of K doesn't agree for those two values. So it's not a constant. So we can say that, decide whether or not it's not a reasonable model, okay? So we can say this model P is equal to 1 minus 4 times the capital F is not, is it KF, sorry, it's KF, K times F is not a reasonable model. Now for working, you need to show this, okay? You need to show that you've used those values from there. Yes, the calculations can be done there for you to check, but you need to show that you've taken at least two values, compared those, and then make that conclusion, okay? All right, another model is P times F is equal to C. Oh, for the same set, okay, for the same table, we got to decide whether this model is okay. All right, use the figures again. They said use the figures. So let's try this for the same data points, okay? So it says P times F is equal to a constant, where C is that constant. All right, use the figures to decide whether or not, similar question, okay? So let's do that again. So the model here is PF is equal to C. So let's do that, okay? For the same one, what color should I use for now? Let me use this one. Okay, so P is 0.99. So I say 0.99 times F, which is 2, should be that C. Is that right? PF is equal to C. And in this case, what do we have? For this case, P is 0.85. 0.85. Let's use the same color. 0.85 times the F now is a 4. Okay, and because we can use the graphing calculator, let's just stick to that. Okay, what do we have? 0.99 times 2 times 2, and you hit that, you get the value C as 1.98. I'm just going to write that thing here. C is 1.98, and here 0.84. Again, I'm going to use that key. So it's 0.85 and times 4 this time, and you're getting 3.4. Clearly, again, oh my god, again this is 3.4, which means again, you know what, C had to be a constant for this model to be true. So again, using the same argument, like I said, show this as part of the working, and then you can say that that model, what is that model, PF equals C, is not a reasonable model. Is it okay? All right, let's move on. C, oh, another model. So there are 3 different models we're playing around with for the same data set, okay? Another model for the data is P. This is a quadratic model, and they've given the values of F 2 to 22, all right? The dashed line, okay, there's a dashed or dotted line. Can you guys see this? Yeah. The dashed line on the diagram shows the graph of this model. Plot the values from the table on the previous page onto the grid. The first 7 points have been done for you, so the remaining ones have to be done. The first 7 have been done for you. So basically you have to plot those points, okay? So again, this is just testing the graphing abilities, I believe. I think that should be easy, right? Should I just skip this part? First 7 they said, what have they done? So there's 1, 2, 3, 4, 5, 6, 7. And you need to do the other one, 16 and 0.02. 16 and 0.02. Let me see where that is. If my eyes can help me, this is 16. This is 16, 0.02, that's here. Is it? Yeah. It should be 16 and 0.02. Okay. What's the next one? It's 18 and 0.02 again. Oh wow. 16, 17, 18. Can you see this is really small? Yeah, 18 and 0.02. Okay. And then what do we have? Then we've got 20 and again 0.02. Wow. 20 and again 0.02. All right. What do we have? 22 and 0.01. 22 and 0.01. So somewhere that's 22, 21, 22. This is 22 and 0.0 somewhere here. Yeah, somewhere there. 2, 4, 6, 8. Yeah, that's correct. Okay, so that's what my remaining 4 points look like. Make sure that you that's 1 point for that. Okay. Yeah, make sure you got it right. So that's the data from that, and this is according to this particular curve, this particular model. Okay. It's a quadratic model. Give the ranges of values of f for which this model, the quadratic model, is a good model and not a good model. Okay, the question basically says for what values of f is on the x-axis. Remember, f was the flow, and p is on the y-axis. P is the probability. All right, so what values of f does this model seem to be good? And just by looking at the graph, okay, it's not by doing any kind of calculation, because earlier we did that calculation. Remember, we said that the model was good or not good based on the data points, you know, just substituting and doing that calculation. Here you're just looking at the graph, and you can see clearly that anything before that point, right, before these points are relatively close to that curve. Look and see that this point is good, this point is close to the curve, this point is close to the curve. It just fits and follows that curve up till there. But the red points that I plotted, okay, that's from the data, that doesn't seem to follow that trend of that curve. So perhaps up until that 7 points as they're looking at. Okay, so 7th point was what? The 7th was 14, and this, remember, is in thousands. Okay, the flows in thousands of meter cube, so it's not 14, it's 14,000. That's how you should write. Okay, so it says it's a good model for, what's the initial value? Let me just check. From 2000, that is. Okay, so it's a good model for f being greater than or equal to 2000 to 14,000, was it? Yeah, 14,000. Okay, maybe you should put the units also. Let me put the units also. 2000 meter cube per second to values of f to 14,000 meters cube per second, meter cube per second. Okay, can you see this? All right, so it's a good model because it just, you know, it's nice close enough to that curve, and then it just goes off. So we can say it's not a good model for greater than 14,000. You can just say for greater than 40,000, because we had the data for 16, 18, 20, 22. So greater than 15, is it 15? even 15 is good. I don't know what those points are. So from 16 onwards you can say, so for f greater than or equal to 16,000 meter cube per second. Not a good model. Clearly by that idea of how well it fits the curve. That's the idea we're using. Clear? All right, moving on. Number 9. Engineers use this formula to model the probability of high river flows. Okay, there's a nice little formula here. Okay, it says P is equal to 3 to the power of a negative F over B, and that to the power of A. Engineers use this formula to model the probability of high river flows. But P is the probability of an event greater than capital F. Okay, that's the flow. Remember, F is the flow. Okay, and A and B are both constants. So A and B are both constants, and we need to show, part A says we need to show that P equals 1/3 when B equals F. All right, B equals F. P equals 1/3. Show that P equals, okay, when B is equal to, let's start with that. Okay, the right hand side has got that F and B, so we'll just start with the RHS, which says when B equals F, what do we have? We've got 3 to the power of a negative, not negative 1, it's a negative, and then there's a bracket, negative, and it's F and B are the same, right? So I'll just first write it as it is, F over B to the power of A, and then that's in a bracket. So this should be equal to 3 to the power of a negative, that F over B, we'll just write it as B over B to the power of A, and B over B is 1, so we'll just cancel that thing off. Okay, and what do you have? What do you have? You got, that's 3 to the power of this is 1, right? 1 to the power of A, this is just going to be negative 1. 1 to the power of any number is just 1, so it's B over B is 1, it's 1 to the power of A, and so it's just 1. Okay, and so we have, this is the right hand side, so the right hand side is 3 to the power of negative 1, which is just 1/3, and so the left hand side must be 1/3. Okay, so let's continue from here. So P must be 1/3. Okay, you see how we got that? We just started with the RHS. B is equal to F. We said B is a constant, A is a constant, that F is that flow, and the P, the probability, is on the left hand side. Okay, so they just said, show that P is equal to 1/3. Simple algebraic thing, replacing B by F. It cancels off, but just keep in mind that 1 to the power of any number is 1, and therefore you'll get 1/3 on the right hand side, which makes the left hand side also 1/3. Give a reason, part B says, give a reason why 8 is the best integer estimate for B. Integer estimate for B when P is equal to 1/3. B is equal, what should be the correct? Okay, use part A, that is this thing, and values from the table for the Missouri River. Okay, so we need to use a table and something from part A. So they say when P is equal to 1/3, remember there's another condition here. It says B is equal to F. B is equal to F. F is the flow. So the integer estimate, they're saying why 8 should be the best estimate for B. Okay, that means the flow is 8. Why should it be? Let's get back to the table. All right, let's just check what's happening at 8. What's happening at 8? The flow is 8. Remember, B is equal to F. Okay, flow is 8, and the probability is 0.26. Okay, and we know that 1/3 is close enough, right? Otherwise this is 0.56 and there is 0.1. 1/3 is closer to 0.26 than the other two numbers, and therefore this must be a better estimate, or what do they say, a more accurate, what do they use the word? It says is the best integer estimate. Okay, so we can say that from the table 0.26 is closest to 1/3. Okay, 0.6, therefore F is 8, which is B, is the best integer estimate for B when P equals 1/3. Clear? So it's just looking at the table and saying that 0.26 is closest to 1/3. Okay, so therefore you take that B, and remember we're using this idea that B is equal to F. That column was for F. All right. Part C. On the axis below, sketch 3 graphs for this model that we've just seen right now. For 0 to 25, the flow being from 0 to 25, use b equals 8. Okay, that's the idea we looked for here from this earlier part. Okay, b is equal to 8, and we need these three graphs. Sketch these three graphs. So just like before, I'm just going to do on the calculate on the laptop here, and then I'll just take a screenshot and put it there. Okay, but you got to actually do the sketch here. Again, let's just see what's similar here. Okay, they've given this as 25. They've not given a, but you know this is probability. Okay, this is probability, so it can't cross 1. Keep that in mind. Okay, and then we can draw the three graphs, and we need to sketch it here. The graph with b equals 8 and a equals 10 is sketched for you. So this is the case where b equals 8 and a equals 10. Let's do it. Okay, and maybe to understand, I'll do all the 4 graphs here. Cool. Let's just switch to the computer now. What I'm going to do is that this is a new one, right? So let me insert a new problem. This is another reason. Okay, it's always good to insert new problems so that you can check your work even before you submitted your paper. You can check your work. I'm going to go straight to the graph page, and the first thing I'll do is that I'll change the window settings. Okay, so like before, I'm just going to make this a -1, or maybe a -0.5. Okay, -0.5. That's just my habit. Okay, I just like to keep a little leverage, as to say. Okay, -0.5 here also. Okay, and here we need a 25, I believe, right? Let's see, 25. Yeah, so let me just keep it 26, just a little additional thing. And here, that I'll keep it as 1. Okay, and yeah, I hope it doesn't cross 1. So let's just keep it as 1 point. I don't know what the graphs are going to behave at 1. Okay, I didn't say it's going to cross 1, so 1.3. Yeah, so I just want to know whether there's a y-intercept or something like that, because this graph out here, as you can see, it apparently cuts somewhere here, no? And I don't know what that value is, so I just wanted to know that. That's why I went a little beyond 1 for the on the y-axis. Okay, all right, let's just enter the graph. First, let's just enter this one as it is. Okay, for this particular graph that they're given, they said that b is equal to 8 and a is equal to 10. So I'm just going to hit tab, and we're going to enter this function. Okay, so the p are our y values, and our x values are the capital F. Okay, so we need to be careful how we enter in terms of x and y. P are our y values. The F1 will represent the P, and the x is going to be the capital F. All right, so keep an eye on that. This is 3, and it's to the power of, right? So this is all raised to the power of. So just use that and get the fraction template. To get the fraction template, we maybe just go one step at a time. Okay, so there's a negative sign. Remember, there's a negative sign. Then put that parentheses. Okay, there we go. And then we need one more of that, and here we get the fraction template, and here we are going to type in capital F. Instead of capital F, we are going to type X, and for this first graph, which is already graphed here, the value of B was 8. Go ahead and insert 8 here. They said A is 10 and A is here. Okay, so this is to the power of, that's why I said it's a very interesting thing, 10. Okay, all right, so this graph is already sketched for us. Wow, that's interesting. This is what the graph was. Looks slightly different now. Oh, it is the same thing. Look at it. So it's quite similar, right? Can you see that? Okay, so my blue graph, let me just get this thing out here. So this is what is given to us, and this is on my calculator here. Now what I'm going to do is that the reason I wanted to show is that I'm going to draw each one using that, because as you saw, it takes some time. Now you can just use this equation and modify it. Okay, so what I'm going to do is that you can copy this. I'm going to just copy this equation. So just double click on that and just copy this, because we just want to make some changes, right? Just copy it, come out of that. Okay, because the question said we got to draw 3 other graphs for those 3 values of A, B remaining 8. Okay, B is going to remaining 8. Just that values of A we need to draw. So let's just hop onto our computer again, and I'm going to say tab for the next one, Control V or Command V, and then let's just change these other values of A 0.5, 0.5, hit enter. There we got our second graph. Okay, let's just move this label somewhere else. Yeah, so that is the graph that is given. That's A is equal to 10. This is when A is equal to 0.5, the red graph. Okay, tab again. Now again Control V. Can you guys see this thing that's going on? Okay, now the value of A is 1. Okay, so hit enter, and the graph is in black. All right, you want to change the color so that it stands out from the color of the axis. You can go and change the color. I'll change it to green. All right, so you got the 3 graphs. Okay, and then hit tab again and Control V again. See it, that's why I said you don't have to, the first time, yes, be careful how you're entering, but then you can just make use of this and edit. Okay, So it's 2.5 they asked. So 2.5, and there we go. You got all those forecasts magenta. So the first graph that was given to us was the blue graph. That was when A is equal to 10. You can see that was the index here. The second graph was when A is equal to 0.5. That's in red. Okay, that red graph. The third graph is what's the third graph? Third graph was the A is equal to 1. Where is that? That's the green graph. Yeah, that's the green graph. And the fourth graph is 2.5, which is this magenta. Okay, so you have to actually draw this. All right, you have to actually draw it out here. You can look at the thing on the graphing calculator, but guess what? You got to draw it. Okay, and they are intersecting a point. I just wanted to read ahead. Okay, this is where our question is, whether they're asking anything about point of intersection. Yeah, it says in part 2, find the coordinates or the points of intersection of the curves. Can you see that? All right, so good idea to do all those things before we bring it out here onto the so I'm just going to hop on here, and we are going to find the point of there is also a point of intersection here. Can you see? That's what I meant. You know, y-intercept, what's going to happen. We need to keep an eye on that, because there's so many of these graphs. Let's see if I can just jump on to the geometry, points and lines and intersection points. I think it's going to ask one graph at a time. So this graph and this graph, okay, so it gave, anyway, all of them are passing through that, so I don't think we need to do for, I mean, if you want, you can go ahead and do it. My hunch is that they're all 1, 2, 3, 4, 4 graphs are passing through these two points. Okay, so it's 8 and 0.333, which was that 1/3, right? We just saw the probability being 1/3 at 8. We already checked that, and this is 0,1, the y-intercept. Okay, exactly at that point. That's why I think I took that a little extra space, right? So those are the 2 points of intersection. I'm going to take a screenshot of this one. All right, so here we go, screen capture, and it will, let me just make sure that it saves, and it will save, and then I'm going to transfer it onto OneNote. So let me just bring up to you guys up to the page here. And where's my OneNote here? The OneNote is here. Where's this, where we are solving? Here we go. I'm going to try and insert it as a picture. And this is my graph. The whole thing comes out here. Is it coming in real time? Sometimes it doesn't sync, huh? The OneNote on the laptop and the OneNote out here. And I just want to make sure that I resize it correctly. Sometimes it takes forever to sync. That is probably just Wi-Fi issues, not the issue of OneNote. Or maybe it's even the OneNote server, I don't know. So that's the graph. You need to actually make sure that you copied on the graph as it is, making sure that you indicate those points. So I think they've got 4 points to just draw the graph. You got the sketch, and the 2 points of intersection are 0, 1. You can write it down. This is coordinates, so so you can write down 0, 1, and what is that? It's 8, 0.3333. 0.3333. Those are the 2 points of intersection. So we've done those 2 questions, and now in part 2 says describe the effect on the graph when A increases and the flow in between 6,000 meter cube per second and 8,000 meter cube per second. Okay, not meter per second, meter cube per second. Describe the effect on the graph. Describe the effect on the graph when A increases and the flow is between those 2 values, 6,000 meter cube per second and 8,000 meter cube per second. Let me jump to that calculator. So between 6,000 and 8,000, right? They said 6,000. So that's 8,000, okay? And 6 should be somewhere before this, right? So describe 6, that should be, yeah. So describe the effect as A increases, when A increases and the flow is in between. So the flow is here on the x-axis, the flow is here, and we're looking for values of A. The values of A are what's differentiating these graphs. Okay, so the blue graph you can see is 10, the value of A is 10. The red graph is the lowest value, right? The lowest value of A is 0.5, and the value of A's are increasing from 0.5. The green graph suddenly becomes 1. The magenta graph is 2.5, and the blue graph is A is equal to 10. So as A increases, that means A is this, then this, then this, then this. So from 6,000, that's the point here, to 8 here. So in that region, if I were to draw it here on the iPad, if I come back to this, just make a note. So we're looking for the region from here, somewhere here, all right, to here for these graphs. So you're just observing what is happening, right? What is happening to the graphs? Is that the question? It says describe the effect on the graph as A increases. That's how the graphs are, you know, as A increases and the flows in between that interval from 6 to 8. Okay, basically what's happening is that the rate of flow is decreasing. You know, the tangent, if you were to look at the graph and just look at the tangent of each of those curves now, the slope of the tangent is becoming more and more negative, right? The red graph, you have to draw a tangent at that, you know, in that region. Okay, the rate, because that's what the slope of the tangent will give you, right? The rate of flow is going to decrease, right? Because it's going to get more and more negative, right? The red graph anyway negative, the green graph more negative, and the magenta graph even more negative, and the blue graph, of course, you know, still more negative. So I think the best way to answer that question is that in that region the rate of flow is going to decrease. Clear? So we come back to our iPad and write that down. So we can say that the rate of flow, okay, if I have a graph, will decrease as A increases. All right. Is that it? Is there anything more? Okay, this is just the last part. Which value of A gives the best model for the Missouri River data on page 12? Which model of A? So from the values of A that's given, which one represents the best? Give a reason for your answer. Which one represents is the best model? Okay, let's get back to our data. What do we have? We got A. Let me show the calculator again. Okay, which one? But we need to see the data, right? So I'm just going to go to the table. Which one will represent for what value of A? Basically, that's what they're saying. Which one will represent? A is equal to the magenta. A is equal to 2.5, and the green, A is equal to 1. I think 2.5, but why? It looks like it's, we need to take some values to verify that. Okay, A is equal to 2.5. Let me just check with some value. That's the best way to do it. Okay, and one sec. Which value of A gives the best model? So we need to just take a couple of values, just as we did in the earlier for the earlier models, to check whether, you know, how good they were or whether they were good or not. So we just have to go back and put in some values for A is equal to each of them and check which one is that. I have a hunch that, you know, because that's right, I don't know, sometimes when I look at the graph I just have this kind of a hunch, but you know, my belief might be wrong, but you can check that and see. But because we're going ahead of time, this is just a substitution, just as we did earlier. How much time have we crossed? Oh wow, it's close to 1 hour anyway. So we're going to stop it because we have done a similar kind of a verification of the model before. It is the same thing that we need to do. Just come back to the table. Okay, use the model for each value of A that you have. For each value of A you have, okay, A equals what was that? A equals 10 might be really too steep. Okay, that might not be a great model, but I have a feeling any of the other models will work for you. And especially if you have done it on the calculator, if you have already inserted on the calculator, all that you need to do is that, you know, we just inserted a new problem. You can insert a calculator page straight up, and because they have already been defined, you can just put the values here and check. Okay, using the table, so that will be directly possible. Okay, so that is how you would check. I'm just going to do one just to demonstrate. F1 is the first graph. Okay, F2 is let's take the one that I had a hunch with. Okay, F4, that's F4, that's where A is equal to 2.5. so I'm just going to say F4. That's the beauty of using this. I'm sharing the calculator screen, so I'm just going to say F4, and I can just put two values. Okay, F4, and remember the X, along the X it was capital F, right? So I'm just going to put capital F, sorry, not like that, 2, the first value in the data set, and I'm going to hit enter. I'm going to 0.966. okay, I'm just going to bring you guys back to this table, and you can see that it's 0.99, close enough, right? And then I come back to the computer. Let's just say the next model was how many did we do? We had a F5 also. What is this? F3. Okay, you can check for each of these models. Okay, so if I say F3 for the same value 2, all right, if I say, yeah, that's off, F2 perhaps, off 2, way off. Now let's take another value. Okay, f4 of, let's say the second value was on the table as 4. If I hit enter, and that is 0.823, and there you go. Okay, I'll show it to you on my iPad. Can you see that we just verified for these two values, the same two values that we took for the earlier two models? Okay, so I just checked that the the f2, which was the magenta model, is close enough to this values. Okay, it's not exact, but the values that we have on our calculator, 0.966 and 0.823, which is pretty much out there. My mom had to just enter right now and put that thing. Didn't realize, sorry, but that's how moms are. Very sweet. Even though you're working, she just comes and puts in another mug, which looks very similar to that of Bonvita. But thanks, but yeah, I don't know how to say. I just got a little irritated. Maybe I should not have. Okay, but that's how moms are. Wonderful. Moms will always be moms, no matter how old you get, right? So there is that Bonvita. She just came and snuck it in. I was just afraid that she'd probably knock off something. So sorry about that little distraction, but yeah. Moms are the best, aren't they? But anyway, what am I saying? I was checking these models, okay, and I think this is a good thing that we took that extra time, okay. So that is f1, f2, f3. You can just use those values because they're defined, and you can put in those values here to check from the table of values that is given to us, okay. We used 2 and 4 earlier, right? We used 2 and 4 earlier on to check whether those models were, this was the first model that we checked, and this was the second model. So this model works the best when A is equal to 2.5. So you don't have to say. So give a reason for your answer, because it satisfies the values of the table. Okay, table values are satisfied. So you've checked with 2 values. Maybe you can even enter those values here and convince the examiner that you've actually checked it, okay, because these things that were done on the calculator, maybe you're not be able to communicate. So maybe you'd have to just put it here and convince the examiner that way. So anyway, I hope this was helpful to you. If you have any thoughts or feedback about this particular modeling exercise, another way to do it or other ways to solve this, do let me know in the comments below. Otherwise, I'm going to see you all in the next weekend.